Hello, ladies and gentlemen. My name is Jiali. I come from Nanjing University of Aeronautics and Astronautics. It's a great honor for me to speaking at this meeting. My presentation is about energy-efficient optimization for joint design of power allocation and beamforming in downlink mmWave communication systems with NOMA. And my report will cover the following aspects: introduction, system model, problem formulation, simulation result, and conclusion. Let's start with part 1, introduction. As we all know, NOMA can achieve superior performance than the conventional orthogonal multiple access by multiplexing the power domain. Due to the large and available bandwidth, mmWave communication is expected to support high data rates. Therefore, in order to take advantage of both the technologies, the studies about the combination of mmWave and NOMA have received more and more attention. Most of the existing works assume that the perfect channel state information is available. However, it can't be guaranteed in practice. Hence, in this paper, we propose 2 schemes of joint power allocation and beamforming design for maximizing energy efficiency with imperfect CSI in the downlink mmWave NOMA system. Next, I will introduce the system model. Considering a 2-user downlink mmWave NOMA system, as shown in Figure 1, we assume that the base station is equipped with a radio frequency chain and an elemental antenna area to support 2 single antenna users. Each antenna branch of the base station has a phase shifter and a lower noise amplifier, and the mmWave channel for the ith user with imperfect CSI can be expressed as equation 1, where ρ is the CSI accuracy. Therefore, the received signal of user I can be expressed as equation 2, where Pi is the transmission power for user I. For the above system, we need to consider 2 cases of decoding orders. Case 1, the signal of user 1 is decoded first by regarding the signal of user 2 as interference. Then the signal of user 2 is decoded after removing the signal of user 1. In this case, the achievable rates of 2 users are given as following equation. The implicit assumption is that the beam gain C1 hat is lower than C2 hat. Similarly, case 2 is the signal of user 2 is decoded first, and the achievable rates are as follows. Therefore, the energy efficiency optimization problem in both cases with imperfect CSI is formulated as equation 5, subject to the minimal rates, maximal power consumption, and constant modulus constraints. We take the optimization problem in second case as an example, since that in the first case can be solved by using the similar algorithms. Introduce a new variable. The objective function in equation 5 can be reformulated into equation 6. According to the first derivative of the objective function with respect to P1, and the beam gain constraint C2 hat is lower than C1 hat, we can conclude that eta EE is monotonically increasing with respect to P1. Thus, the optimal P1 is its upper bound, which can be obtained by the rate constraint of user 2 as equation 7. With the optimal P1, we can rewrite P2, and the energy efficiency optimization problem is formulated as equation 8. Where Pmin is obtained by the rate constraint of user 1. We can observe that when one of P and the beamforming vector omega is fixed, the resultant problem can be efficiently solved. Therefore, we adopt the block coordinate descent method to solve this optimization problem. In particular, we decompose the problem equation 8 into PA problem and the beamforming design problem, and then solve the power allocation problem for given omega and solve the beamforming design problem for given P. First, for power allocation problem, we can use concave converse producer to solve the problem. By adopting the first-order Taylor expansion, a Loy bound of eta EE at the tth iteration of CCCP is as follows. Then the power allocation problem can be formulated as equation 10. With the aid of Lambert W function, the solution P tidal is expressed as equation 11. So the optimal solution of the above problem is given by equation 12. The algorithm for power allocation is summarized as algorithm 1. For a given P, the beamforming problem in problem 8 can be expressed as equation 13. We adopt the successive converse approximation to address the problem. Introduce two new auxiliary variables. Then beamforming problem can be relaxed to the following problem. In what follows, we adopt SCA method to address the problem 16. Accordingly, we need to solve the following converse optimization problem at each iteration of SCA. CVxTOR is used to obtain a suboptimal solution. To satisfy the CM constraint, we make the CM normalization for each element of beamforming vector omega as follows. As a result, we summarize the first joint design scheme in algorithm 2. Furthermore, we propose an alternative beamforming design which has low complexity. The beamforming problem decomposed from the optimization problem file is reduced to equation 16. Without considering the constraint of minimal rate, the beamforming problem can be formulated as equation 17. Then a suboptimal solution can be obtained. Due to that, beta belongs to 0 to 1. We can use the one-dimensional search method to solve the beamforming design problem. In conclusion, the second suboptimal joint design scheme is summarized as algorithm 3. The following are simulation results. Figure 2 indicates the system EE with different schemes and the impact of imperfect CSI on the EE. with the CCCP-based PA scheme. The beamforming design of proposed scheme 1 based on SCA and that of proposed scheme 2 based on one-dimensional search method. Scheme 3 means search for the face of each engine of beamforming vector. You can see from the figure that the system EE decreases along with the decrease of rho. This is because the channel estimation error results in the increase of interference when decoding the user's signals. The performance of both proposed schemes is close to that of scheme 3, and proposed scheme 1 outperforms proposed scheme 2. However, as shown in Table 1, scheme 3 has the highest complexity because it retires n times one-dimensional search method. The complexity of proposed scheme 1 is much more than that of proposed scheme 2 because CVX has poor computational efficiency, which results in longer runtime. Therefore, there is a trade-off between the schemes. This figure gives the EE performance of the mmWave NOMA system on the different beamforming schemes. Design beamforming scheme 1 refers to SCA-based design. Design BF2 refers to beamforming design based on one-dimensional search. FRAB and MRTBF solve the power allocation problem on the given beamforming. The proposed scheme has better performance than the other two schemes, since the beamforming vectors of FRAB scheme and the MRTBF scheme are independent and not optimized with power allocation jointly, which fortifies the effectiveness of two proposed schemes. Figure 4 displays energy efficiency comparison on the different rate constraints. The system EE decreases with the increase of minimal rates, and the higher minimal rates are, the more system EE is reduced. This is because proposed scheme 2 is formulated without considering the rate constraint. The higher the minimal rate is, the more performance loss it will bring. Besides, the gap between two schemes is bigger with the increase of minimal rate, since the rate constraint has more effect on proposed scheme 2. That's all for the simulation results, and finally, I'd like to make a conclusion with this presentation. We studied the joint power allocation and beamforming design problem to maximize energy efficiency for downlink mmWave NOMA system under imperfect CSI. The proposed schemes are developed by BCD method and decomposed the origin optimization problem into the power allocation subproblem and the beamforming subproblem. Specifically, for the power allocation problem, we derive the closed form solution of CCCP by Lambert W function. For the beamforming design problem, we obtain a suboptimal solution by SCA, and also derive a suboptimal beamforming utilizing the one-dimensional search method, which has lower complexity. In addition, the simulation results prove the fact that our two proposed schemes have effective on the system EE performance. That's all of the presentation. Thank you for listening.